Now let's look at the converse of the perpendicular bisector theorem. So remember, converse is when we're flipping the hypothesis and the conclusion of a conditional. So now we are being told that the point is equidistant from the endpoints of a segment. Okay? So if a point is equidistant from the endpoints of a segment, then we can conclude that it lies on the perpendicular bisector of the segment. So here we have D. If we know D is the same distance from A as it is to B, so the blue lines here have equal lengths, then we know that D is actually on this perpendicular bisector. So this line that you see intersecting segment AB is actually going to pass through D. That's what that converse is saying. And of course, with every theorem, there is a proof. So there is a proof of the perpendicular bisector theorem. So copy this down, pause, and when you're ready to go, hit play. In order to complete this proof, we're going to do something that we don't really do all the time, which is using the perpendicular postulate. We've used the parallel postulate in a couple proofs, but here we're now having to apply the perpendicular postulate. So to do that, remember that in this proof, we know that AC and CB are equal. So we could actually mark that. We know that AC and CB are equal. Okay? This is what we know. And actually, these red markings here really are what we're trying to prove. So I'm going to put red circles on them instead of those red tick marks, because we don't know they're congruent yet, right? That's what we're trying to prove. Now, using the perpendicular postulate, we are going to draw this line in so that it is perpendicular to AB, and it is passing through C. So in order to prove that C is on the perpendicular bisector of it, we need to show that AP and PB are congruent. We already know it's on the perpendicular line, but we have to know it's also bisecting. So we have a few things that we need to do in order to prove that. And you want to think of triangles. Notice there's two triangles here, right? Think of congruent triangles. We just talked about congruent triangles last chapter. We have our ways to do that. So if we could get these two triangles congruent to each other, then we could get AP and segment PB congruent. So switching into congruence, we're going to say that segment CB is congruent to segment CA by our definition of congruent segments. Actually, that should be definition of equal segments, right? Because we're starting with them being equal. Let me change that to equals. We're starting with them being equals, and then we want to show them congruent, right? Okay. Now, we also know, remember, keeping on those congruent triangles, we know that CP is congruent to itself, okay? And we also know that we have a perpendicular line. So the definition of perpendicular lines, we know that we've got two right angles there. And using the right angle congruence theorem, those right angles are congruent to each other. Now, what is this a setup for? If I have a right angle, that means I've got a right triangle. I have the hypotenuse, which is located opposite the right angle on each side. Those hypotenuses are congruent. And we have another side of the right triangle congruent. That looks like a setup for HL, hypotenuse leg. In order to use HL, we do need to state that the triangles are right triangles. So that's my next step. Using definition of a right triangle, I know that triangles CPA and CPB are right triangles. Now the triangles are going to be congruent through HL theorem. Hypotenuse leg theorem. Corresponding parts, we now know that segment PA is congruent to segment PB. And the definition of a perpendicular bisector is that, yes, we know it's perpendicular, but second is that it's going to intersect at the midpoint. Well, if you have two segments that are congruent and share an endpoint, then we know that that common endpoint is the midpoint. So P is the midpoint of segment AB, and then we're finished. C is on the perpendicular bisector of segment AB by the definition of perpendicular bisector.